(32) CPS geometry. The proof for Riemann hypothesis, Part 1. Let's consider again the domain of the CPS geometry. As we have seen throughout this series, this is the manifold, determined by the infinity of infinitesimal identical spheres, distributed according to the close packing of spheres arrangement. We have shown in the previous video, if we consider the diameter of the spheres as being equal with 1, then the distances between any two points in this manifold is equal with the square root of an integer number. A closer examination of the square and the hexagonal arrangements of identical spheres reveals that they are in fact the same arrangement. One can see that a simple rotation of the square lattice arrangement becomes the hexagonal lattice arrangement, and vice versa. Any 2 points, belonging to the CPS distribution of points, determine a line pattern. The smallest distance between 2 points on a line provides an efficient way of characterizing each line. This distance is the unit of measurement for the line. The distance between any two other points on the line is a multiple of the unit of measurement. As seen before, fascicle of lines emanating from a central point, which have the same unit of measurement, form well-defined lines patterns. In the previous video, we have presented and investigated the lines patterns corresponding to the first 13 square root numbers. Can one continue this process and find lines patterns for the next, let's say, 1000 square root numbers? At this stage in our investigation, we can only state that the distance between any 2 points in CPS can be expressed as a square root of an integer number. Let's inverse this fact, and now ask the following very interesting question. Are there points in the CPS arrangement such that the distance between them is equal with the square root of any natural number? Or, in other words, can we find 2 points in the CPS arrangement such that the distance between them is equal with the square root of any integer number? To better define and understand this question, we will introduce a numerical function, which we will call the CPS function. 1. Let us mention first an obvious fact: the CPS patterns are seen in exactly the same way, from any point in the CPS arrangement. All the CPS points are identical with each other. 2. Let's consider next a point in the CPS arrangement, and call it point O. What is true for point O is also true for any other CPS point. 3. Now, for any square root number, n, we want to determine how many points are there in the CPS arrangement, which are situated at a distance equal with the square root of n from point O. This is the CPS function. 4. The domain of the CPS function is the set of the square root numbers. 5. The codomain of the CPS function is the set of natural numbers. Indirectly, we have already met this function when presenting the line patterns corresponding to the first 13 square root numbers. From there, one can easily see, for example, that CPS of 1 is equal with 12. CPS of square root of 2 is equal with 6. CPS of square root of 7 is 48, and CPS of square root of 12 is 24. Let's try next to find a general, numerical expression for the distance between any 2 points in the CPS arrangement. To do this, let's consider first 2 parallel CPS planes with an underlining square lattices. As shown in a video, in the beginning of this series, the square lattice planes have a periodicity of 2. If the diameters of the spheres are equal with 1, then the smallest distance between 2 such similar planes is equal with square root of 2. Let's consider 2 such planes that overlap perfectly over one another, and let's consider point A belonging to the first plane, and point B belonging to the second plane. Let's also consider the planes to be z-planes apart. Then, the distance from point A to the second plane corresponding to point B is equal with AH. This distance can be expressed as AH equals z multiplied by square root of 2. Point H and point B belong to the second plane. The distance from H to B can be expressed as HB is equal with square root of x square plus y square. Now, the distance from point A to point B can be expressed by the following general expression. AB is equal with square root of x square plus y square plus 2 multiplied by z square. This is equivalent with the following general expression. The square of the distance between 2 points belonging to 2 overlapping square lattice planes is given by D is equal with x square plus y square plus 2 multiplied by z square. Let's remember this expression for now. As we have shown already, the CPS arrangement has the property that every sphere in the arrangement can be considered as being determined by the intersection of 3 orthogonal planes. Let's consider 2 arbitrary points in CPS, point A and point B. As said above, each of these 2 points can be considered as the intersection of 3 orthogonal planes. The set of the 3 planes corresponding to the point A are parallel with the equivalent planes from the set of 3 planes corresponding to the point B. There are 3 ways to go from point A to a plane corresponding to plane B, one for each plane determining the point B. These 3 ways are determined by the 3 lines starting in point A, and orthogonal on each of the 3 planes, through B. The configuration of the CPS arrangement guarantees that at least one of these 3 orthogonal lines always intersects the corresponding plane in a CPS point. Or, in other words, any 2 arbitrary points from CPS belong to 2 overlapping square lattice planes. This allows us to extend our established expression for the distance between point A and point B to any 2 points belonging to the CPS manifold, without doing any change to it. This expression is true for any 2 arbitrary points from CPS, and it is the expression we will use in the next step of our investigation. Of course, x, y, and z are natural numbers. D square is also a natural number. A closer look to this expression reveals that our initial question is equivalent with the following question. Let n be a positive integer. Are there triplets of integers, x, y, and z, such that n can be expressed by the following sum? X square plus y square plus 2 multiplied by z square? This is now a problem of number theory. To solve this, we look back to 1770, when Lagrange proved the following theorem. Every positive integer is the sum of 4 squares. Later, It was also proved that a positive integer can be expressed as the sum of three squares, if and only if it is not of the form 4 power r multiply by 8 multiply by t plus 7. Armed with these two theorems, we are able to proceed with solving our problem. It is easy to observe that our expression can be written as the sum of four squares, two of them being identical. N is equal with x square, plus y square, plus z square, plus z square. So, our case is somewhere between the cases described by Theorem 1 and Theorem 2. With a bit of manipulation of the demonstration of Theorem 2, we arrive to our final conclusion. A positive integer n can be expressed as the sum of four squares, two of them being identical, if and only if n is not of the form 4 power r multiply by 16 multiply by t plus 14. Let's see some of these numbers. If r is equal with 0, and t changes, one gets the sequence 14, 30, 46, 62, 78, 94, 110, 126, 142, and so on. If r equal with 1, and t changes, one gets the sequence 56, 120, 184, 248, 312, 376, and so on. And finally, if r equal with 2, and t changes, one gets the sequence 224, 480, 736, 992, and so on. What are these numbers? What do they mean? First, let's mention that these numbers are the zeros of the CPS function, introduced above. Going back to the definition of the CPS function, one can see, for example, that CPS of 14 is equal with 0. CPS of 30 is equal with 0, or CPS of 224 is equal with 0. We are now in the position to answer our initial question. Are there points in the CPS arrangement such that the distance between them is equal with the square root of any natural number? The answer is no. One can never find 2 points in the CPS arrangement such that the distance between them is equal with the numbers corresponding to the square root of the zeros of the CPS function. For example, there are 2 points in the CPS arrangement which are square root of 14 apart. Or there are 2 points in the CPS arrangement which are square root of 30 apart. And so on. This is quite a remarkable finding. In the next video, we will examine some of the meanings and the significance of this discovery to mathematics and science.